Yeah. Hello, everyone. I think we'll start the meeting now. Hello. Good to see so many people turning up. Really good. As you can tell, there's a new addition to the EV group here, little Finn, named after the veins on a heatsink. Yeah, so hello. There we go. And to all those people in internet land, there he is. There we go. All right, well, enough of the frivolities, the serious business of electric vehicles. Yeah, welcome everyone, nice turnout. It seems that the battery end of the technology is something that sparks everyone's interest, if I can use the pun. You'll hear all the latest current technology from Paul this evening, if I can throw in another pun. Yeah, we'll get on to that in a minute. First, I'd just like to let people know about how you can stay connected with the EV group. We've got a Facebook open group, which is the ATA Melbourne EV Branch. So if you go to ATA Melbourne EV Branch, then you can see everything's happening, and we post all the latest bits and pieces up on the FaceCrack site. So feel free to peruse that and post up anything that you want to put up there yourself. Also, you can catch up with us on the ATA, Alternative Technology Association website, so that's ata.org.au, and just follow the links to this Melbourne EV branch. For those that have missed any of the past seminars that we've had here, then you can see them all on our YouTube channel. So again, just go to ATA Melbourne EV Branch on YouTube, and not only can you see us broadcasting live, but you can have a look at past seminars over the last couple of years. We also have the Renew and also Sanctuary magazines that are put out by the ATA. Well worth a read. You can get them here from us for cheap, or from your news agents for more expensive. So feel free to grab a copy here, because the money that you give for these magazines here goes to this EV group. So so we can have more upper class tea and bickies later, and other things. Okay, first. Apologies for those that might have turned up last week and found us all not here. We had a wrong date on it. We're just in the process of changing over from our old secretary, who now has a new job as mother, to our new secretary, Adrian Cohen. So a big applause for Adrian Cohen. He's been with the EV group since Adam was a lad, and he's done an excellent job. Always here with the AV, consistent, good man, and looking forward to his secretarial involvement. Let's see, what else? Also, past events. I haven't really got much of a list of past events that's been going on, but what has been brought to my attention is that Tesla has unveiled their supercharged network across the USA and had a launch a week or two ago, where they drove a couple of their cars across the US, and apparently it all went very well, and so hopefully that dispels some of the range anxiety fears that some punters may have. The Tesla, as you know, is a quality car, and quite a range, and if anyone wants to buy me one, come and see me later. I'll gratefully accept it, no questions asked. as far as future events, the only thing that I know of which is half related would be a Velo in the Park event that will have some electric bicycles and electric tricycles at it in Adelaide on the 8th of May. Now, I'm just wondering if anyone here has any knowledge of past or future events that we could be alerted to and spread the news.
Either holding its annual EV festival in Melbourne this year. So it looks like it'll be in Coburg on the 25th and the 26th
Of
October.
25th and 26th of October for the Australian Electric Vehicle Association's AGM and festival and seminar, right? And so Coburg, hey? We could.
Everyone turn up, bring your cars.
Yeah, well, we'll all be there, and more for sure. So yeah, that's something to look forward to. The AEVA do a good job and well worth supporting. Okay, now any news about things that are happening in people's garages? Yes.
One outside, you can have a look at a Mitsubishi PHEV. Right down the street.
A Mitsubishi
PHEV.
PHEV.
Plug-in hybrid.
Oh, very nice.
Oh,
Oh, wicked! All right. Well, make sure that we that we get a bit of a look at that before it's all over this evening. Fantastic.
Won't get to see it next month because my wife will be somewhere to book with it.
Right, fantastic. Oh, well done.
Take the trailer for 2 weeks.
And so, and how has it been performing for you so far?
Good. 25k range loaded.
Mm-hmm.
Ton and a half. About 40 plus riding around highway, otherwise electric wise. Springs back in electric. What I didn't read anywhere is they run down the highway in mechanical drive.
Oh.
Once you get over about 65 k's, it actually, if you're in battery mode, it runs full time. But once you run out of battery, then the motor starts up and it shows that you're mechanically driving the front wheels, unless you need more power, in which case then the back motor kicks in. And if you really want more power, everything kicks in.
Right. Okay.
It's quite excellent.
Yeah. Right.
Quite impressed with the way it works electrically. It's an electric vehicle first and a hybrid second.
Right.
Lovely. Well, certainly
like
like to.
when you burn in, like you're running out of battery.
Yeah.
When you get to a town, and there's that bit of slowing down or whatever, it's quite often enough to do half a k or more in electric mode, particularly if you're going slow, even a kilometre or two. So yeah, it's very good. I've only had it today, so.
Oh, okay.
I've done 500 k's in the last 2 days.
Oh, still giving it a good workout already. Fantastic. Oh, that's lovely to hear that the Outlanders got a Guernsey here amongst the group. Yeah, we'll all love to stick our head under the bonnet and see how it all looks and feels.
What was the price?
50,000. You can buy the luxury one for around $5,000 more if you feel inclined.
All right, fantastic. Oh, that's really good. Any other past, future events or any stuff around the garages? Anyone working on their vehicles at the moment? Repairing, upgrading, converting? No, it's getting a bit cold now, I think, to be in the garage. When you don't have a big, thirsty ICE engine keeping you warm. All right, well, I think that my part of the evening is over. Is there any other things that I've missed? Not that I can think of. Right, well, I'd just like to introduce Paul Paton, who's been a long-time member of the EV group, a very industrious and innovative person who I call my battery guru, because anytime I need to know something about a battery, why it's working the way it does, or more importantly, why it's not working the way it should, then Paul is the one who's been able to help me out. I've much respect for his knowledge in the world of batteries, and we're pleased and privileged to be able to hear what he's got to say today. So, Paul, please step up and take it away.
Okay. Thank you, Dean.
No worries.
Thank you. Thank you, and welcome you all tonight to those. I've done a presentation on some of the different batteries that are used in electric vehicles. We're going to look at a bit of the history of the batteries that have been in vehicles, and then move on to what's available on that at the moment. So as we can see here, go on to the first slide. As we know, the electric vehicle industry started in the turn of the century on those, and they were building electric cars around that time. On those, it was actually more popular than the petrol car at that time. And I've got a video here of an early electric car. This is one of the Detroit Electrics. So I managed to find a video of it on those so we can see one going. A car like this operates on lead-acid batteries. So these were the first batteries that were used in electric vehicles. So this is the type of performance that you can expect, you know, from a lead-acid type vehicle. It's got the door closed. So someone's restored this lovely antique car. So lead-acid batteries were the first practical battery system that could be used in an electric vehicle. Good for limited range, low speed. Stop that one. Yep. So back to the presentation. So the very first battery that was used was a lead-acid battery, very limited range, about 40 kilometres range. That car was a 24-volt system. Okay, we can go on to the next slide now. So I'm going to show some of the later type battery systems that are used in vehicles, but I thought I'd bring the slide up first before I show you some of the newer vehicles, just to show you what the energy capacity is of the different types of battery systems. The lead-acid battery here starts at 40 watt-hours per kilogram. The nickel metal hydride, which has already doubled that capacity, so you can get twice the range or twice the energy out of a kilogram of batteries. We then moved to lithium phosphate, which was another early type of electric vehicle battery, going up to 100. This one here, NMC, is actually lithium, nickel, manganese, cobalt. This is quite a common battery that's used now. It's used in the Leaf and in the NiMH on those. So it's actually the most popular, I think, of the current lithium-ion type batteries. Then we go up in energy again to the lithium cobalt. This is the lithium cobalt was the original lithium-ion battery that was developed for laptops and for consumer appliances. On those, and it was developed quite some time ago, 15, 20 years ago, and it's still it's a powerful, very useful type of battery to use in a vehicle. And then, of course, top of the range at the moment now is the NCR battery, which is manufactured by Panasonic. It's actually an improvement on lithium cobalt, or it is really a lithium cobalt battery, but with a few other changes to it. Aluminium has been added into the formula, but the NCR, well, that's the battery that's used in the Tesla Model S. So so you can see how its power density then compares with some of the other the batteries. That's the best available at the moment. I think we'll go on to the next slide.
What does NCR stand for?
It's an abbreviation that I'm not really sure that Panasonic have given to it. The NCR type batteries have additional protection in them. The polymer layer in them is less resistant to heat, so they can be run hotter than lithium cobalt batteries before they catch fire. So there's been some additional safety precautions that Panasonic has put into the lithium cobalt battery when they developed the NCR to make it safer than what the lithium cobalt battery was. So now we're moving to 1999, and this is when electric vehicles really started to get moving. General Motors made the EV1. I've picked the Generation 2 EV1 because this is the very first car that used the nickel metal hydride battery. So as we saw from the previous graph, we've already doubled the energy density of the battery. We've now gone to nickel metal hydride, and this is an example of the nickel metal hydride type range. We've now got a range up to 170 kilometres, and acceleration of the car is, similar to what a four-cylinder sedan would do. So if you could play that video on that one. No, it's the wrong video. It's the EV1. Nope. 3. It's that one. Yep.
Los Angeles got a 2 million cars sold every year, like the skyline, evil ranking, yet small. LA is dying at the scene from the tyranny of the V8 engine.
So this is Los Angeles in the 90s, when they wanted to do something about pollution.
America's big 7 automakers must producing sub-zero emission cars. GM got there first. The electric car is here.
And here it is, General Motors EV1 electric, or as they say in California, the Volkswagen. This is the car the oil companies and other car makers have tried to stop. It's cost GM near $500 million and is state-of-the-art technology. So what we're going to do is we're going to take all the sparky air out of the car and thrust of LA streets and see just how long those batteries last.
So this is a nickel metal hydride type car.
It will accelerate to 60 in about 8 seconds, and they actually have ungoverned one of these doing 90 miles an hour on Hollywood sort of flats. This is governed because it's California, law assessed to 80 miles an hour.
But it was quick enough to give a daisy smooth and Volvo G5 the absolute fright of his life.
Here we are at the traffic lights. And the nickel metal hydride car still was fast enough to win.
For those Amy are effective enough to want to know, the EV1 weighs 3,000 pounds, that's about its battery. It has the aerodynamics of a fighter jet with a landing gear down, literally. And its practical range, even though the app saying it's 90, is actually about 40 to 50 miles per drive. There's one guy apparently bought a Polaroid snap to a dealership to show that he'd actually achieved 101 miles on full charge. I'm not so lucky. So what do I think? Well, it's actually very quiet, very refined, very quick, and very drivable. In essence, that's all good little car. But the battery sucks, the ranges are falling, and if you had to buy one, it would cost a whopping £35,000. But let me leave you with this thought. 10 years ago, mobile phones were the size of suitcases and cost £2,000. Today they're the size of calculators, and they're giving them away. Make no mistake, the days of the internal combustion engine are definitely numbered. Yes.
Yes. So that was the 1990, or was it? Nearly 2000 on those, when that was the type of car that GM was able to produce at that particular time. So nickel metal hydride battery, you see the range, 170 kilometres, reasonable acceleration on those, so that was where we were up to at that time. We'll go to the next slide. And then the introduction of the lithium cobalt battery. The lithium cobalt battery came out of, well, consumer electronics. It was a high energy battery, went into laptops, went into mobile phones. It was a real step forward on those in battery development. And those, so the Alika in 2004 was able to be built with a range of 310 kilometres, very good acceleration. And this is a little bit about the Japanese who developed one of the first lithium-ion cars. Should we play that video?
A streamlined car flashes by at over 300 kilometers per hour. But there's no sound in an engine.
The Elika has 8 motors. It's 8 wheels with a hub motor in each wheel.
Motors and batteries. Has more than 600 horsepower. It's a genuine supercar. In February 2004, serious test drives of the Elika began at a track in Tochigi Prefecture. 400 kilometers per hour is even higher than the speeds reached in Formula One. Kilometers per hour at just 7.0.
So this was an acceleration test against a Porsche.
Doing 138 kilometers per hour. The Porsche doesn't reach 160 kilometers per hour until the 9.2 second mark.
So even with no gearbox, the electric vehicle was still able to out-accelerate a Porsche up to 160 kilometers an hour. Now this is interesting. This is some of the batteries that we used within the vehicle. These are lithium-ion or lithium cobalt batteries, one of the standard batteries of the consumer industry.
Lithium-ion batteries, which offer good storage capacity and power, were refined in Japan.
But I also thought it was interesting to note that the batteries actually slide underneath the body. So like this was one of the first cars where they put the batteries in the floor, under the floor of the car.
The car has 320 of these batteries. Large lithium-ion batteries are not yet mass-produced, so the number needed to power one car currently costs almost 20 million yen.
Lots of batteries and a reasonable amount of weight.
Recent automakers have shown only limited interest in electric cars. The company employs more than 30,000 workers who make enough lithium-ion batteries.
So with the Elika car, they were looking for a company that could supply them with batteries. And they actually went to China, and they found out that the same development, the same thing was happening in China.
Developed lithium-ion battery for cars. Enough of them to power one car cost about 2 million yen, much less than in Japan. The most competitively priced lithium-ion batteries in the world are powering this company's attempt to create a cheap electric car that can win in the marketplace.
So in China, companies like BYD and that were looking at developing electric cars for the Chinese market.
The battery maker has accomplished all this in just 2 years. This speedy development has been spurred by China's severe air pollution problems. Electric cars help limit emissions. There's a big demand for them in China.
Okay, let's go back. So that was what they were capable of building in 2004 with the invention of the lithium cobalt battery. We'll go to the next slide. And then 2011, the next car that I'm looking at is the Nissan Leaf. I've chosen Nissan Leaf because it was a very popular car. I'm going to do the Roadster first. We skipped a slide, okay. The Roadster was the first commercial vehicle to use lithium cobalt batteries. So in the Roadster on those, the battery system actually went behind the back seat. It was in a module behind the back seat. And I suppose it was when Tesla went to the Model S and they put it in the floor that they were starting to get problems with something piercing the battery from below and causing a battery fire. But in the Tesla Roadster, it was actually enclosed behind the back seat. It was in the back part of the car. But this is a car typically that's built with a lithium and cobalt batteries, range of 320 kilometers, and good acceleration. So by 2008, this is where we got to with cars and with batteries. And the car really represents the battery. You know, the design of the car, how well the car performs is dependent mostly on the battery. Can you show this video? Go to this one now.
For some people, Tesla is going to be all about the numbers. 200 miles of range, almost 7,000 lithium-ion batteries. 0 to 60 in 3.7 seconds. Over 1,200 cars already sold to environmentally conscious customers who are looking for a way to reduce their impact on the planet. It has the kind of column twist that this electric motor does. By the numbers, it's not that.
So here's to describe a little bit what it's like to drive a Tesla on those, and the EV grin, the electric power that you get from the motor.
Not only is it fast, it's enjoyable to drive. There are plenty of fast cars out there that aren't a lot of fun to drive. This is not one of those. What primarily makes it fun is that character of the electric motor. This is a completely different, completely new type of performance. With this car, we've got the instant torque of the electric motor. We've got the very futuristic style and very futuristic interior. And it feels postmodern. It just feels right. To me, this is a better and more enjoyable car than a Lotus Elise. Works awesome.
So now we've got a range of 320 kilometres, excellent range, and 0 to 100 k's in 3.7 seconds. So beating the performance really of the best petrol cars at that stage. The next slide. Now we've moved to 2011, and a new battery has been introduced around this time. The lithium cobalt, of course, has been around for quite some time. But now we've got a new battery coming out. This is the one that we call the tri-metal battery, or lithium, nickel, manganese, cobalt. It's another form of lithium-ion chemistry, and it has a longer life than lithium cobalt. So the life expectancy you would have of these batteries would still be in the order of 8 to 12 years. You would expect to get out of a battery like that in a vehicle. Whereas the lithium cobalt batteries, 3 to 5 years, 8 years if you're treating the battery carefully, you know, is the sort of life that you expect. But that wasn't really long enough. It wasn't long enough for what the consumer and that expected. They wanted a longer life. They didn't want to have to think that in 5 years they would have to then buy another battery. You know, why have an electric car in that case? Whereas these particular batteries, the tri-metal batteries on those, they've been introduced into e-bikes as well as cars. You know, are a longer life type battery and middle of the range, reasonable performance on those but longer life. So now in the Nissan Leaf we've got a range of 190 kilometres. So they've brought the range back on those to a more reasonable level, but they've made the car more affordable and reasonable acceleration, you know, similar to a four-cylinder type car. So if you could play that video. So this is the sort of car that you get with a nickel manganese oxide battery.
Here are the numbers. That motor is an 80 kilowatt unit powered by 48 separate lithium-ion batteries, like what's in your laptop, with a total of 24 kilowatt hours of storage capacity, 107 horsepower, 207 foot-pounds of torque. You see, these are torquey machines. It's a 3,400-pound car to 60 in about 7 seconds. Now, range is a funny word. Click on that on Nissan Leaf site, and you don't get a number. You get this convoluted looking thing, this graphic.
It's very hard to predict the range on an electric vehicle because it really depends on how you drive it.
Depending on terrain, conditions, how you drive, even the weather.
So that's one thing that we find, like we build battery packs and that for electric bikes and things, and you know, and people say, well, what's the range? Well, it really depends on how you ride it on those. You know, we can quote a range, but it's only an estimate. So we'll go on to the next slide. Now we have the NCR batteries, the ones that we're talking about on those, which is the best of the batteries that are currently available at the moment. Lithium, nickel, cobalt, aluminium on those. The Panasonic have added aluminium to the formula to make the batteries last a bit longer than what lithium cobalt did. So they're looking at a life of 8 to 10 years. That's what we'd typically expect with the Model S. But they're still a high energy battery, a battery that has the highest energy density of all of them. With a battery like this, you know, Tesla's now capable of producing a car with a range of 460 kilometres, excellent acceleration, you know, a really good car. So once these batteries are now being developed, this is the type of car that they're capable of building. So we'll have a look at that video.
Tesla believe it can lead a revolution and change the face of motoring forever. It's the first ever mass-made premium sedan powered purely by electricity. Designed to have speed and range, and not a drop of gas.
Our goal is to create an electric car that is the best car in the world and show that that's what an electric car can be.
A family sedan that can go from 0 to 100 in under 6 seconds, and further on a single charge than any other electric production car. Designed to match the top gasoline competitors. The Model S has free space for a floor upwards. They use thousands of small lithium-ion cells, similar to laptop batteries. Thanks to these regular batteries, the companies say the Model S has achieved a top range of 480 kilometers. The high-performance battery pack is formed with over 7,000 small cells. They're organized into a flat layer with specific groupings of positive and negative.
10 years from now, Tesla will change the perception of what mainstream cars can be. And it'll become clear that electric cars truly are the future.
So now we've got the nickel, lithium, nickel, cobalt, aluminium batteries. So on those, the latest formula that Panasonic has produced. I suppose Tesla are using the small batteries, the 18650 format, mainly because they can be manufactured very cheaply on those. They can then use the mass production manufacturing that is currently being used for laptops and for other battery purposes. And that very small battery also is able to dissipate heat very well. Because it's small in size and it has a large surface area, it's able to dissipate any heat that's generated within the battery. So it's an additional safety requirement as well. But so that's the batteries, and that's the current best batteries and that are available at the moment. Go to the next one. Now I'll put this one in because this is a typical home conversion. You know, we've been talking about cars that have been commercially produced. But this is a car that someone's produced at home. They put a few LEFP04 batteries in them, which are actually designed as for the stationary energy industry. They put those batteries in, and just to show what sort of performance they were getting and what they've done there. So this video will show more of a homebrew type setup and what's happening with homebrew type cars.
Only then could the actual electric conversion start. All major components were chosen, purchased, and installed in the next couple of months. And even though the electric Samba is currently operational, it is still very far from being done. One of the main reasons for all the work ahead is that one of my original goals for this vehicle is not yet met. I originally set out to build an EV that would drive 100 miles or more between charges. In its current form, the Samba has given me a maximum of 65-mile range, even though there are things I can currently do to improve on it. I'm cutting down drag by installing 20 of the 23 windows.
Just about cut all the frame out of the body.
My range goal is to change the current 21 kilowatt-hour lithium-ion phosphate battery into something bigger, but yet lighter.
He wants a bit more range.
The problem is that even though now it's considered old technology, first generation lithium, it's still still rather expensive. The energy density is not the best with 90 to 110 watt-hours per kilowatt. That means that my 22 kilowatt-hour battery comes in at 480 pounds and occupies all the area where the old gas tank used to be, plus most of the cell's floor space. If I want to meet my 100-mile range target using lithium iron phosphate, I will have to spend roughly another $7,000 and get really creative finding space for all those additional cells. So the alternative is to look at another chemistry, like the one used on the best electric car today. That would be lithium cobalt cells used by Tesla, first on the Roadster and now on the Model S. They use mass-produced cylindrical 18650 cells commonly found in cordless power tools and laptop batteries. They are small in size, very light, very powerful. The cost is about the same as lithium iron phosphate. The advantage of lithium cobalt is that it comes in about half the weight and size, allowing my someone to go further using a battery with roughly the same physical size and weight of the battery. So Tesla has designed very clever ways to build safety features into the battery packs. One of the most unique and clever safety features is a cell-level fuse used in every battery. Each one of the 7,000 cells used in the battery.
There's a fuse on each cell of the Tesla battery.
With a cell mount, which measures the Tesla battery pack pictures all on. It looks like they use a very simple voltaic-wired fuse on the cell.
When they assemble a Tesla battery pack, they put a fuse in every single cell.
I just need to test wires with different anodes so I can one that goes inside the battery. So it looks like I have found one fuse cable.
So it's experimenting with different wires to work out the fuse, the particular fuse that he wants to use. And he's going to put a fuse in every one of those cells. Lots of batteries, isn't it? It's a big pack.
We almost lost a wheel right here.
So that's interesting there. So someone who's built a homebrew car with LiFePO4 batteries wanted to try and extend its range. Is it on a limited budget? It's only got so much money to spend, and also so much room within the car, and then trying to work out how he can increase the range in that of his car. And that particular guy is actually using second-hand laptop batteries. He's getting batteries from I don't know where, and then testing them. On those, testing them for internal resistance, testing them for their capacity on those, and then building up battery packs and that out of those. So that was one way of looking at extending the range on that of his car. So if you don't have the budget for new batteries, there's always other sources, there's other places than that you can find them. We'll go on to the next slide. Also from that slide too, the individual fusing that Tesla do on their battery packs. When you've got so many batteries like that, all are connected in parallel on those, and say in the Tesla Model S, if you get an impact from underneath the car and one or two of the batteries are punctured or damaged in some ways, the individual fusing then just disconnects those cells. And because there's virtually 100, 200 of them in parallel, it would really make very little difference to the pack. Or if one of the cells was to break down or blow for some particular reason, you know, the fuse will just take it out of the circuit, and then the others will just continue on. So that's one safety feature that Tesla have put in their cars on those with all of the cells, you know, lots of little batteries. They individually fuse them. Okay, so I'm going to go back to this slide now. So this one really shows the story. As you can see there, the different energy densities that are available for the current batteries that are available on the moment. Nickel metal hydride is quite close to lithium iron phosphate, very similar in energy density, a slight increase through there. Lithium phosphate has the lowest energy density of all of the lithium chemistries. It's a battery that was actually designed for the stationary storage, for battery backups, for storage packs that are used in uninterruptible power supplies, and it's used as a storage battery. And then we have NMC, which is the nickel, manganese, cobalt. This one is actually the most popular of the current batteries. It's used in the IME, it's used in the Leaf, and a lot of the other car manufacturers. Actually, the motorbike, it's the Brembo, or Bremer? Bremer, is it? Bremer, yep, the new motorbike now. They've changed to NMC batteries now in the Remo in the current model on those. So this battery is taking over at the moment. It seems to be the most economical in that in the commercial market. And then you have the higher energy batteries that are available as well, which is lithium, cobalt, and Panasonic's NCR. There actually is a competitor to Panasonic in the NCR. Samsung also make the same high quality battery as well. I think theirs is called ICR 18650. So they do have a competing manufacturer. We'll go on to the next slide. So this is a bit explaining what a lithium-ion battery is. They're rechargeable batteries, as we know, because you have two types of batteries. You have non-rechargeable and rechargeable. And we're really mainly interested in the rechargeable ones. They consist of an anode, dissolved in carbon, and then they have a cathode material, which is the lithium cobalt, or one of those materials that we were talking about. So those two materials is what makes the battery work. Because what a battery is it really just stores energy in a chemical form. So in this case, it's electricity. It's storing electricity due to its chemical process. Go to the next slide. If you're interested, there's the reaction, the chemical formula that makes a lithium-ion battery work. But the main thing I want to talk about this is it's reversible. This is how it works. The chemical reaction goes one way when it's charging, and the chemical reaction goes the other way when it discharges. So that's how all batteries work, and it's a particular chemistry that's used in the battery that gives it its performance. Next. Next, I wanted to talk a bit about BMSs on those and some of the BMSs that are in the battery packs, because it's another issue that's associated with the vehicle. Yes.
On the point of the charge and discharge, do the different chemistries have different efficiencies in the charge-discharge cycle?
Yes, they do. The lithium-ion chemistries, pretty well across the range, have almost 100% efficiency in their charge and discharge, whereas nickel metal hydride had a much lower efficiency in charge and discharge, maybe 70 or 80%. So nickel metal hydride batteries, when you charge them and discharge them, they get hot. And you might have noticed that quite often there are fans and that in the nickel metal hydride system. But the lithium-ion battery was an improvement there. It's very close to 100%. And you can charge a lithium-ion battery and it does not heat up. But if you charge it rapidly, like in a half hour, trying to do a quick charge on it, it will produce some heat. So the BMS. Well, the BMS has three functions within the battery pack. There are three things that are required for lithium-ion batteries to keep them healthy. Low voltage protection, to stop discharge if one of the batteries falls below its minimum operating voltage. If you run a lithium-ion battery to zero or just past zero, it'll destroy the battery. But even then, we don't want to run it near zero. We want to have a safety factor there. So there's a minimum operating voltage. High voltage protection, to protect the battery when it's being charged, because some of the individual batteries in that pack might charge faster than others on those and their voltage rise is too high. So the BMS also has to give protection on the battery pack when it's charging, so that individual batteries don't overcharge. And then the last function of the BMS is a balance function. And what the balance does is to keep all the battery packs at the same voltage by distributing the charge throughout the entire pack so that all the batteries have a similar rate of charge in them. The balance function also is very important to keep the battery healthy, because if a battery goes out of balance, when you charge it, some of the cells will go too high, or if the battery's out of balance, when you discharge it, some of the low batteries will actually go flat. So balance is an important function. Now here we are, we've got two different types of batteries, and I'm comparing the actual charge curves for two different batteries. With the LiFePO4 battery, once it's charged, it reaches about 3.55 volts. And then if you continue to overcharge it, it will very quickly rise above 4 volts, whereby the battery will be starting to be damaged. It'll start to age prematurely from overcharging. So at 100% charge, it's at about just on 3.5 volts. Whereas all the other lithium-ion batteries, which is lithium cobalt, LiPo, the NMC type batteries, they have a different charge curve. As they approach 100% charge, their charge curve is quite flat, and they can be overcharged quite considerably before any damage occurs. So this charge characteristic is very important because it does show a safety factor in the lithium-ion and the lithium cobalt battery when it's overcharged, whereas with the LiFePO4, if you overcharge it, unless the BMS protects the battery, it'll be damaged very quickly. Damaging voltage at 3% overcharge. Here with the lithium-ion battery, it'll take an overcharge of 24%. They actually make lithium-ion batteries of this type that are 4.35 volts, that are actually designed to be charged to 4.35 volts, whereas the standard lithium-ion battery charges to 4.2 volts. So there is safety within the chemistry to actually produce batteries that charge to high voltages in that particular chemistry. Go to the next one. And then we have the discharge curves, and that of the two different batteries. And they're quite different as well. The lithium-ion battery starts, this is the lithium cobalt and all the other chemistries. They start at 4.2 volts, and then they discharge to around 3 volts. They're considered flat, between 4.2 and 3 volts. Whereas the LiFePO4 has a more flat discharge characteristic. It's fully charged at about 3.4, 3.45 volts, it's fully charged, and then it's considered flat at around 3 volts, 3 to 2.8. It's considered flat with a LiFePO4. But the reason that I've shown this curve is to talk about how the BMS operates on those. And one of the most important functions of a battery is it has to be kept in balance. Because if the battery's not in balance, if there's more charge in one cell than another, when you fully charge the battery, you're going to have problems of overcharging, and when you fully discharge it, you will have some cells that will go flat. So the actual balance of the battery is extremely important on those in maintaining the life within the battery. Now I've quoted here 40% depth of discharge and 60% depth of discharge, just as 2 points of reference on the curve. And we can see with the LiFePO4 battery, at 40% discharge, the battery is at 3.34 volts. At 60% discharge, it's at 3.32 volts. So we're only get a difference of 0.02 of a volt between 40 and 60% discharge on the battery. With the lithium-ion battery, 40% discharge, it's 3.2 volts. 60% discharge, it's 3.63 volts. It's a much wider difference in voltage, 0.11 of a volt, 0.02 of a volt. And why I've mentioned that is the BMS now is trying to keep that battery balanced. It's trying to keep the battery within balance. But between 40% discharge and 60% discharge on the LiFePO4 battery, the 0.02 volt difference will not be picked up by the BMS. Commercial BMSs aren't able to pick up such a very small difference in voltage. So the BMS will not be able to keep all the cells completely balanced within the LiFePO4 battery on those, whereas in the lithium-ion battery, because of the extra difference in voltage, the BMS will be able to easily keep the battery balanced. So an LAF-PO4 battery could have individual cells, individual batteries in the pack 20% out of balance, and the BMS function wouldn't correct it. So this is one of the problems that you have with LAF-PO4 batteries, is that it's very difficult to keep the battery balanced on those, and the BMS systems can't keep them balanced. And as the battery drifts out of balance, then wear starts to occur on individual cells within the battery, and the battery then starts to fail early. So the discharge curve, even though the lithium ion has a much wider range of operating voltage, and you might get really good performance when it's fully charged, and when it's going down to nearly flat, you know, your motor's going to run slower because of lower voltage. It is an easier battery to keep in balance and to keep functioning properly. Go on to the next slide. So some of the conclusions from that. With LAF-PO4 batteries, the BMS must be of a very high standard and has a lot more stress on it than in the other lithium-ion chemistries. Lithium, cobalt, NMC, on those the voltage ranges are wider, the BMS has a lot more function to work in. And therefore, there are more BMS-related failures in LAF-PO4 batteries than in the other chemistries, due to the batteries drifting out of balance and the BMS not being able to correct it. So this is what we've found, that in a lot of the cars that have been made by people with LAF-PO4 batteries, usually hobbyists that have made their cars on those, the batteries aren't lasting the 10 or 15 years that they're supposed to, because they're faulty. There's been failures that have been occurring within 1 year, 5 years. A good BMS system might go for the 15 years of the battery. But there's been a lot more failures in the LAF-PO4 batteries. And if you were to try and use a simpler BMS system, such as a balance board on that, on an LAF-PO4 battery, it will be more likely to fail. There are some people who build cars with LAF-PO4 batteries, and then they say, well, I'm going to balance it manually. I'm not going to bother using a BMS on those and there. And the LAF-PO4 battery actually is far more critical on having a BMS and keeping it balanced. Can we go back 2 slides? Back again. First of all, because of this one here, the actual overvoltage characteristic. If you try and charge an LAF-PO4 battery without a BMS system on it, some of the cells will spike, what we call spike in voltage, and that'll be damaged if you try and 100% charge it. So it requires individual cell monitoring with LAF-PO4, and the BMS system must be a lot more sophisticated. Otherwise, damage will occur very quickly within the battery. Okay, we'll go forward. So the last thing I wanted to talk about was a new development in batteries. Well, it's not actually that new. It's been around for a while. They're going to now try and start using these within vehicles. This is a totally different concept of battery called the metal air battery. The metal air battery is lighter than the other type of batteries that we use because it only has one metal electrode. It only has the anode within the actual battery itself. The cathode of the battery is actually air. It uses oxygen from the environment to catalyze with the metal and produce the electricity. So we're already looking at 1/3 of the weight because there's no other electrode in there. But this is a new design of battery that they're now testing and trying to get work with electric vehicles. Now, all the current metal air batteries are not rechargeable. They haven't been able to make a rechargeable type metal air battery that works and that lasts on those. At the moment, they're all not rechargeable. So metal air batteries are used in hearing aids, they're used in a number of other products, but they're now looking at using them in a vehicle. But they can be recharged. You can recharge a metal air battery by replacing the metal plates. So like having a battery which you use it till it's flat, and then you pull the metal plates out of it and replace them, like a mechanical recharge system. Put a new plate in it, and then it then goes off for its next range. So researchers are trying, they're working at the moment to try and create a metal air battery that's rechargeable. Go on. Now Tesla have taken a patent out with the US Patents Office for a car that uses a metal air battery. And people were wondering, you know, why would they do that? Why would Tesla take out such a patent? But they have, they've lodged one, and this is the patent that Tesla's lodged. We have our motor, our drivetrain, we have our controller here, which is pretty standard in a normal vehicle. Then we have a non-metal air battery pack, which would be lithium ion, naturally, in a car. So you'd have, this would be your standard battery pack, and then you have a second battery pack that's metal air. So you'd have two batteries within the vehicle. And so you'd wonder why they do that. Well, the reason they do that is the second battery is actually a range extender battery. It's a battery to enable the vehicle to go a long distance, whereas the normal lithium-ion battery provides the current to run the motor and gives you the shorter, the normal range. So the metal air battery is used to extend the range of a lithium-ion car battery. And that's the concept of how they would use a metal air battery at this stage, until they work out how to make them rechargeable. And go to the next slide. So Tesla had lodged that patent, and at the same time, another company in Israel has actually produced a car with exactly the same technology. So I don't know what the patent's got to do with anything, because someone else has already built one, or has built one. And it might have been actually just after the patent was released. But this here is a car made by Finergy. It has a tri-metal battery in it, nickel, magnesium, cobalt, and also an aluminium air battery. By using the two batteries, you now have a range of 1,600 kilometres. So that's a real game changer, isn't it? And it's been tested, and it does have that range. So electric cars are going to be able to be produced with longer ranges. Acceleration, 0 to 100 k's in 8.5 seconds, which is a bit slower than the Nissan Leaf. On those, it's not got the current performance, but reasonable. But where it exceeds is in range. So I'm going to show a video that will explain the metal air battery and how it's used in a car.
The CEO founder is today's master of chemical engineers. Just show me how it works. Okay, this is the battery here in the boot. Yeah. And what we have here is a 1,000 miles is extending on top of the energy you daily charge from the grid. So you've got a lithium ion battery over in there, and you've also got this aluminium battery, and the aluminium, by reacting with the air and the water, it recharges the lithium. That's great. Actually, what you see here is the word anode from aluminium, and this is.
So there's the aluminium plate that makes the battery work.
Here, when you consume more of the aluminium, it becomes so thin. So you see the delta in weight.
So it uses a reaction between aluminium and oxygen from the atmosphere.
And this is how we do 1,000 miles in a weight of 25 kilograms. So let's talk about aluminum. Aluminum is the most available metal on Earth's crust. It is 8%, and we find it as alumina. And by charging it, actually electrolysis, we are creating.
So when you produce aluminium, you're actually storing chemical energy in the aluminium.
And if we look at this not as really to construction material, as to store it. So we need to know how to discharge aluminum on time when we really need it. In order to do that, we have to have water, aluminum, and air and grid using our proprietary air-diffused cathode, a very thin layer, and I'll explain to you how it works. The interesting part is that the aluminum hydroxide, which is the rust of aluminum, let's say, can be recycled. Actually, we can reuse it. It's not thrown away. It's either be recycled back to the aluminum industry or diverted to a secondary market that
can use this material for other reasons. So, a normal battery, and we spoke about many technologies.
This is a normal battery. I was talking about the cathode. This is the cathode. This is the anode.
Within the package. And when 60, 70, 80% of the volume and weight usually lies in the cathode, and we can see it on the left side. And it holds some kind of oxygen to do the reaction, to release the energy from the anode. So we say, let's throw it away, 80% of the weight, and let's slide in this very thin cathode. And this is actually what we have here. So this thin layer actually doing the task of the cathode just in time, breathing air from this side, and the catalyst on the other side sucking the water inside the battery, and actually release the energy from aluminum. Volume, 1 barrel of gasoline can allow a car to drive about 3,500 kilometers. 1 barrel of aluminum, in terms of carrying it around the wall, can allow you
can go 14,000 kilometers on a barrel of aluminium.
So what about, instead of having this, we will have about 50 kilometers lithium worth of energy, and maybe 400, 500 worth of electricity that can be released by water that you can pump in. And this is the car that you can see outside, and I ran out of time, right?
So let's go back to the slide, and I better explain it a bit more, because this concept is totally different. So he's quoted 1,600 kilometres range for the car on those, but I suppose he's made a statement there. He said, well, we can go really long range on this car. But what you would do, you would have a lithium-ion battery that would have a short range, 60, 80, 100 kilometres or whatever it is. You know, you'd have a short range one. And then a aluminium-air battery that would give you your extended range. Maybe 200 kilometres, 300, 400, 600 kilometres, you know, it depends on what you want to do. Because we don't need 1,600 kilometres range out of the car. But what by having the two batteries, what that achieves is that you can have a lighter car because the lithium-ion battery is smaller, and when you need extended range, the aluminium air or metal air battery, and that is used. So it's like two battery systems within the same vehicle. So that's the concept of the car. To explain a little bit about the aluminium air battery, the aluminium air battery does have an electrolyte in it, which is potassium hydroxide. So there's water, there's electrolyte within there, but it gets its oxygen from the atmosphere. So virtually there's a catalyst within there that enables the aluminium to oxidize in the atmosphere. And as the aluminium is oxidized, it produces electricity. So we're now converting chemical energy into electricity, which is just what any battery does. But in this case, it's the energy that's stored in aluminium, and then once it's oxidized, that energy is released. And that aluminium can then be recycled. It's now hydroxide, aluminium hydroxide in solution. It can be reclaimed and recycled and put back into the cycle again. So I like the concept of this battery.
Just to get this straight, you discharge that battery, you throw it away, you put the batteries in, right?
No. What happens is the actual plate is eaten away within the battery, the aluminium plate. So the aluminium plate has to be replaced.
And you do that, just slide
Yeah, it'd be a mechanical type of recharging rather than electrical on those. So yeah, a new plate and that would need to be put inside the battery. It might even be a little bit more involved in sliding it in, but that would be nice if you could. But yeah, it's a different way of recharging a car. See, at the moment they're not able to produce rechargeable metal air batteries. They haven't got a design that works, so that's why they came up with this alternative. Yes?
As a battery for air, environmental air, into itself, and it's still you see also, for example, if the carbon involved in an accident and rolled over upside down, it produces so that it won't be.
Well, the actual cathode of the battery is a permeable membrane. So it's actually a membrane that this particular company, Finergy, has developed. We'll go back 2 slides. No, forward 1. Yeah, I think we'll stick to there. Probably the best way. So that's a safety requirement, and yeah, I think you're right. You should be concerned about that because there is liquids within the battery, but it has a permeable membrane that allows oxygen to enter from the atmosphere, but the liquid not to get out. Yes, Tom?
Manufacturing of aluminium is very, very energy intensive. So when you quote energy capacity stored in aluminium or various metals, you should refer it, or compare it with energy that is used to manufacture this aluminium from whatever ore, like it is. Because this is the only difference. Only the difference between the two is actually meaningful.
Very true, isn't it? So we probably have to look at the efficiency of the aluminium manufacturing industry and to see, how much of that energy that is used in manufacturing aluminium actually ends up within the metal, and that as such.
And how much is we can reclaim, and also how much energy it takes to recycle it back, to produce aluminium. So we have to look at the whole cycle rather than have a snapshot, that could be misleading. Another issue is that when we put electrical energy to produce aluminium by electrolysis or whatever other process that we use, the energy that comes in to produce aluminium is actually from fossil fuel in Australia. So the footprint that we make using aluminium, is very serious because the energy efficiency of our power station is about 20% fossil fuel. So it means that from the coal, ground coal, 80% of energy actually escapes through Rhino's chimneys, and only 20% goes into the electricity.
Yes.
So by producing aluminium,
that's the same issue that we had with charging up your electric car regardless of the batteries.
That's right. Unless you are like me, powered by sun and wind, then I have no worries. I can charge for that.
Hydro in Tasmania produces aluminium, same in Canada. So it's the source of the electricity that you're looking at, not affected is coal in Victoria that you can't sell. That's no good.
Yes, but we have to see the whole picture rather than only the potential of aluminium.
Very valid point.
Yes.
We need to see a bigger picture. The whole picture.
Yes, that's right. This is new technology, which is only just being developed as such. And yes, you're right, I'm showing the batteries in use within a vehicle. It's very true, isn't it? We have to look at, if we want to make it sustainable, we have to look at all of the cycles, don't we, to make it sustainable as such on those. But yeah, just making the point that a lot of energy is stored in aluminium. And aluminium air is only one type of metal air battery. There are actually other types than that as well.
Lithium air was, much higher rated than aluminium.
That's right. Yes, it seems that they're building an aluminium air battery because they've been able to get the technology to work, and it's something that they've been developing. But I'm sure we'll see other ones come along as well. Let's go forward there. So here we have, this is the theoretical maximum energy densities that are available with these particular technologies, with these chemistries and that, I should say. So you can actually make a battery by using any of the metals reacting with air. So zinc air is another well-known one. This is the one that the hearing aid batteries and that are made of. Zinc air batteries have been available for quite some time, and actually it's the lowest energy density that you look at the moment. But then again, some of these materials are quite abundant in the earth, so on those, so that's another issue through there. So you can see the maximum. So our current energy density we're getting from batteries now, that's the NCR batteries that are used in the Model S, 258 watt-hours per kilogram. So you can see the scale, the difference in that we're looking at there. We're looking at 4 times to 20 times, the energy density on some of these batteries. So in the future, the energy density of a battery, like the problem we're having now, is probably not going to be an issue. on those. They'll be able to build electric cars which will have batteries that are quite light on those, and be able to, to be light, and those. It's probably more to do with cost and which one performs better. But anyway, so those are the theoretical energy limits that are available with metal air batteries. That's it.
Any questions?
Yeah, any questions from the floor, even about BMSs or batteries or anything?
The 18650 and the 26650 surgical power, they have an in-built BMS. Some of them do. Do you know anything about them? Are they any good?
Yes.
You repeat the question.
Yeah, I'll repeat the question. I was asking about 18650 and 26650 batteries that have a built-in BMS and that built into the battery, and are there any good on those, was the question. Well, yes, you can buy these batteries, and they're called a protected battery. You can buy 18650 batteries that have a protection built into them. I haven't used them. They are quite good on those. Whether they're suited to high current applications, I'm not sure. But the protection, you can buy these lithium-ion batteries with a protection model actually built into the battery. Next question.
Yeah, you spoke about BMSs for lithium iron phosphate.
Yes.
Do you recommend a good BMS for yourself?
A lot of the work that I do is on electric bikes and a little bit on electric cars, but mainly electric bikes. So with lithium iron phosphate, you do need a BMS system that has all three of those functions, which is the high voltage protection, low voltage protection, and balance function on them. So yeah, I would look into the BMS that you are using and make sure that that it was a good quality one that would work in that. No, I don't have enough experience to recommend one.
With this problem with the BMS not being able to balance very well, how can you overcome that? By not charging the car so much, or charging it to full every time you use it?
Yeah, by not charging it to full every time you use it, by charging to 80% rather than to 100%, and then also not discharging it all the way, so leaving 20% of the capacity within the battery. Those two ideas are a good idea to do with that battery system. It really just depends upon how well the BMS has been manufactured on those and whether it's operating correctly within the battery. I would say also doing internal resistance checks on your battery every year, like going through and checking the internal resistance of each individual battery and replacing batteries that are showing signs of age, because you'll get a cascading effect through the battery if one of the cells fails. So probably just doing a bit of maintenance and making sure that it has a good BMS system already.
So what are you looking for with the resistance, internal resistance?
We're looking for the internal resistance not to be, say, 30 or 40% higher than original manufacturer's specs. So around that point, I'd start to become concerned that that particular battery needs to be replaced out of the pack. Yeah.
Fuel gauges on lithium iron phosphate batteries must be really difficult to get right, because the voltage difference between fully charged and fully discharged is very small. That must be another reason to go to a steeper curve, if you like, for the discharge curve.
Yes, that's right. A voltmeter will still give you an indication of your charge on your lithium-ion battery, on your lithium-ion phosphate battery, though the voltage range is smaller, so you're looking at less differences in voltage. So you can still use a voltmeter on a lithium-ion phosphate battery and see how charged it is. But a lot of the commercial systems that monitor the batteries actually have a current sensor in the battery lead, and they measure how much power has actually been taken out of the battery. So instead of the meter actually working on voltage, it actually measures how many watt hours has been taken out of the battery, and then gives you a percentage reading on the dash. Yes?
I think Prius batteries are being recycled by Toyota as stationary batteries.
and probably others as well. And there's talk also of using them within by utilities for various purposes of the grid. Do these other chemistries lend themselves to those sorts of reuse? And why is it that batteries seem to be having to remove the car when they apparently have lots and lots of service life in them? What is it that they stop doing satisfactorily?
It's a very interesting topic because, yes, it's very much, I've had a good look at this, and it's very true. They are, well, first of all the current chemistries can be used for that purpose. You can take a battery out of a vehicle and then use it in a stationary storage application, and you'll get many more years life out of it. You probably get double the amount of life out of it than what it had in the vehicle. So they can be used for quite a long time in stationary applications. The main reason that they take them out of vehicles is a vehicle requires quite heavy currents for acceleration and for cruising at reasonable speed. So the batteries and those are being operated under quite high currents within a vehicle. And the internal resistance, what happens as a battery ages, and I'll talk about lithium ion and lithium ion phosphate, all those ones, is they don't lose their capacity, they don't lose their ampere hour capacity as they age. What happens within the battery is that the internal resistance of the battery rises, and when you try and accelerate with a vehicle, you get voltage drop on those occurring within the battery. On those, so as the batteries reach their end of life, the performance of the vehicle starts to drop off. On those, you don't get the acceleration. You do also lose a small amount. I'll say you will lose a small amount of the ampere hour capacity due to fracturing of the electrodes and that within the vehicle, within the battery, but not a lot of the ampere hour is actually lost. It's actually the increase of internal resistance that is the issue within the vehicle. So that battery can be taken out of a vehicle, put into a stationary application where it's not stress as low, where it might be run well below its normal C capacity rating, and it can be used for many, many more years on those, and it'll just gradually age, what we call age. As there's a calendar life on batteries, as they age and get older, their internal resistance starts to rise. The nickel metal hydride battery actually has different characteristics when it ages than lithium ion. Side reactions occur with the nickel metal hydride batteries, and they develop very high leakages and other problems as they age. But the lithium ion battery especially is very good at aging. It can be put into other applications. Just a bit like the Samba project there, where he was using used laptop batteries and testing them and wanting to build a battery pack for his car. Those batteries that he was testing, most of them had good capacity, but some of them were quite poor with their internal resistance.
Any cost estimates for those batteries? Costs.
Yep, cost. I was asking about cost differences for the different types of batteries. Yeah. Well, you're talking about the lithium, the different lithium batteries as such. No, I didn't have a cost analysis on them, though we can see some that are obvious leaders, and that's the NMC battery, the nickel magnesium cobalt battery. I would say companies such as Mitsubishi and the IMEV and the Nissan Leaf, they chose that battery for its performance and obviously for its cost characteristics as well. The lithium cobalt batteries in 18650s are also lower in cost as well, and Tesla chose them for that reason because they could obtain them at a lower price. Yes, yeah, that's it.
Fascinating presentation. Thanks so much, Paul. Two questions, if I may. Can you talk about how these batteries perform in a hot environment, i.e. where the environment they're in is already hot, like the Australian climate, as opposed to a European or North American climate? And secondly, could you talk a little bit about the current battery technology that's used in electric bikes?
Okay. Well, first of all, temperature. The temperature related to the batteries, and temperature does have a huge effect on batteries. So that was a good point to bring up. Tests have been done on vehicles such as the Nissan Leaf. On those, there was a study done on Nissan Leafs all around the world, And they found that there was an enormous difference in the life of the battery depending upon the temperature of the environment in which the battery is used. Nissan Leafs that were in Arkansas in America, on those, which has one of the highest average temperatures, you know, annual average temperatures, we're only achieving 3 or 4 years life for a Nissan Leaf battery, which is an NMC battery that we were talking about. Whereas that same battery, when being used in Norway or in another colder part of Europe, on those they're achieving calendar lives of 10 to 12 years. So it's quite a big difference, isn't it? An enormous difference in there. And that's been a concern for Nissan for selling cars in America and into hot climates, that the Nissan Leaf battery was not suitable, you know, while was giving a poorer life in hot climates. And I think that could also be extended to other forms of lithium batteries as well, even though I haven't seen any real research in that. But also lithium-ion batteries, lithium cobalt and that, they have a calendar life. They age so much per year. And that calendar life is actually influenced by the temperature of the environment that they're kept in. So if you keep your lithium-ion batteries in the fridge, you know, they would last, you know, a long time. And if they're in a hot climate, and that they might. Now, there's one more point I wanted to talk about temperature as well. It also affects the current that the battery can produce, and the amount of power that the battery can produce. Some of the cars and bikes and that, when they're driven in a cold environment, you'll notice a loss of performance on those because the battery is not able to produce as much current as what it can in a high temperature environment. So the chemical reaction slows down within the battery in lower temperatures, and you know, if you're driving your car and it's in freezing weather, on those you will notice a difference in performance with lithium batteries. The second part of the question regarding e-bikes, wasn't it? On those. And e-bikes, on those, most of the e-bike batteries that are built use lithium cobalt cells. On those, they're the lowest cost, the highest energy, they're the lightest batteries, and that to be used within e-bikes. So lithium cobalt is very popular in that in e-bike batteries. But we're now starting to see e-bike batteries change to NMC as well, the tri-metal batteries, because they have a longer life within an e-bike battery than lithium cobalt batteries had. You know, they'll be able to produce e-bike batteries that last 5, 7 years on those, whereas the lithium cobalt e-bike batteries have a hard life. Some of them only last 2 or 3 years sometimes. Yes, Tom?
I would like to maybe add some temperature effects. 2 years ago we had a presentation in this room from CSIRO scientists about thermal effects on lithium batteries. And his message was, or research result was, that lithium battery heated above 50 degrees loses some percentage of capacity permanently every time it is heated above 50 degrees.
Okay.
When it's cooler, the cooler temperatures result in loss of capacity, but this capacity is fully restored when the battery is warmed up to our temperature. So 50 degrees was the message, you know, like the threshold above which, you know, like there is some, you know, like a damage to the battery capacity.
Oh, that would make sense.
This is, you know, like a result from CSIRO, from a public presentation at ATA meeting, you know, like maybe 2 years ago. Yeah.
Oh, good. Thanks for that, Tom. Yes.
Tesla released the S with a 40 kilowatt hour, 65 and 85 kilowatt hour battery.
Okay.
They dropped the 40. And I can't, perhaps you get a nightmare as to how much difference roughly in costs it would be between 65 and 85. And why don't they make them all 85s?
Oh, okay. Well, first of all, Panasonic make 3 standards of NCR 18650 batteries. So they make, well, the A and B is the most popular type, and those one's 2.9 ampere hour and the other one's 3.4 ampere hour. So I would assume in the longer range, the larger battery, they're using the more expensive, the 3.4, you know, the A batch, you know, the best batch on those out of the batteries and those from Panasonic. So I think the smaller battery was dropped the 60, did you say, was it 40?
40 was
the 40, yeah. So the smaller 40 I think was dropped because customers didn't want it on those and they just didn't really get any demand for it. People were buying the higher 2 batteries. But of course it must be more expensive because you're building a larger battery, so the cost of the battery is scaled with the size. Yes?
Can you speak at all about costs and advantages and disadvantages of different types of stationary applications, like a lot of people want to add storage to their house?
Yeah, I'll talk a little bit about that. On those, of course, well, I haven't had a lot of experience in that area, only a bit. On those, of course, the lead-acid battery has been the ruler, you know, in stationary applications for quite some time on those, and you can buy deep cycle lead-acid batteries that are long life on those, that will last 10, 12 years on those, you know, not like a car battery that only lasts 3 years or so. So they've been the ruler for quite some time. But LiFePO4, the lithium iron phosphate battery, is now starting to move into solar and stationary appliances because it is the lowest cost of the lithium ion chemistries. It has a very long life. It can last 15, 18 years in a stationary appliance, you know, application like that. So your cost return there with the longer life on those. So LiFePO4 batteries are now starting to be used more in stationary in some of the newer systems. Though I still think the lead acid one is still very good in comparison in price. Yes, the back.
LTO batteries you haven't mentioned, which are sort of one step below lithium phosphate, which apparently they take they're 2.3 volts, if I'm got it right, and they take a very high discharge or charge current. They're used now for SMA and some people in the grid.
Oh, yeah.
Load shifting.
So does anyone know that type of battery, the LTO?
Lithium titanate is actually the
Titanate or Tinate?
LTO is the sort of abbreviation.
I suppose I haven't mentioned it because it doesn't seem to be used in vehicles.
It's in the middle of the one step below lithium phosphate as far as its density goes, but it's a bit tougher and it'll take a very high input and output current.
Oh, good. No, I don't know the battery, and no, I haven't put it ahead in my display.
There's a few listed around. Sanyo makes some, but yeah, finding information about them is not that. There's quite a bit there, but not as much as all the other chemistries.
Okay, can't help with that one. No, maybe last question.
Another question. I have some comments about stationary energy storage because I've got some personal experience with it because I live off grid, you know, like there. And a few years ago, I decided to install nickel iron batteries. Nickel iron batteries, they have a lifespan maybe 100 years, 200 years. They don't mind being, you know, totally discharged, and you can't really damage them, you know, any other way, you know, like. And if they lose too much capacity, you just change the electrolyte. Yeah. So one of the experiments I did, I installed it to my GP, a lady, you know, like who has no idea about, you know, energy efficiency or anything, and she's discharging those batteries daily, you know, like to zero, you know, like, and they don't die, you know, like so. The batteries that Edison constructed 100 years ago, they are still working today.
Yes, I've heard of them used in telephone exchanges on those. They're quite good. Well, we're going to have some supper now, and those to have a chat over a cuppa and things. So Dean's going to wind the meeting up.
Yeah, so thanks again, Paul, for display. Yeah, so thanks, Paul, and we'll go next door and have some tea and biscuits, and you can mine Paul for some more information and have a look at his a few of the batteries and inverters and little bibs and bobs that that he makes industriously on his kitchen table. Okay, thank you.